Okay, so welcome back everyone to our discussion on graph theory. In the previous video, we discussed the preliminary concepts in order to carry out the process of solving shortest path or fastest route from starting point to destination. Now, the process of solving shortest path or fastest route is called the Dijkstra's algorithm. So the Dijkstra's algorithm is a method of determining shortest path or fastest route from starting vertex to destination vertex. In our discussion, we will use or designate S as our starting vertex. Also, we will restrict our graphs to simple, meaning there's no multiple edge or loop. Connected, this means that there is always a path from one vertex to another, and positive weighted, which means that the labels of the edges are positive. Now, the graphs that we will discuss could be directed, meaning one way, or undirected, meaning two ways. Now, with the development of mathematics and technology, there are much more complicated algorithms in finding the shortest path or fastest route from starting vertex to another. So what we will discuss in this video is a much simpler version of that algorithm. Now, in order to carry out the Dijkstra's algorithm, we need to have or discuss these concepts. First, in every step of the Dijkstra's algorithm, we have the state of a vertex. The state of the vertex has two components. You have the distance value and the status label. The distance value represents an estimate of the distance of the vertex from the starting point. So this is just an estimate, and this distance value gets updated each time a step is carried out. Next, the second component is either permanent or temporary. So we mentioned that the distance value of the vertex is updated each time a step is carried out, and we stop whenever a vertex has reached permanent status label. So when a vertex reaches permanent status label, this means that we have found the shortest distance of that vertex from the starting point. Now, aside from this state of a vertex, we also designate one vertex as current vertex. At each step of the algorithm, one vertex is designated as current. Now, we will discuss how to choose current vertices in the next slides. Okay, so now let's discuss an example. So for our first example, I want you to copy this graph. Make sure that you copy the vertices, the edges correctly, plus the weights. And for this video, I want you to carry out the steps as we discuss the process of Dijkstra's algorithm. If you need more time to copy the graph, you may pause the video. Okay. So for our first step, it is called initialization. So what is this initialization? We will assign 0 distance value to the starting vertex, say S, and label it as permanent. So recall that the state of the vertex has two components. You have the distance value and status label. Next, we will assign infinity distance value to all other vertices and label them as temporary. And then finally, we designate vertex S as current. So let's go back to our graph. So this is our graph. This is the starting. According to the first line, assign 0 distance value to the starting vertex and label it as permanent. So you have 0 and then permanent. I will just use P for permanent. For the second line, we will assign infinity to all other vertices and label them as temporary. So we have infinity temporary right here, infinity temporary, and then we do this to all other vertices. Okay, and then for the last line, we will designate vertex S as current vertex. So we designate this one as current. So this ends step 1 of Dijkstra's algorithm. Now let's go to step 2. Okay, for step 2, we will update the distance value of the neighbors of the current vertex. Again, we will update the distance value of the neighbors of the current vertex. So how do we update? To each vertex adjacent to the current vertex, so in other words, neighbors of the current vertex, we will update distance value. Of course, shorter distance replaces longer distance. If the distance is longer, then that means the shorter distance stays. So let's go back to our graph. So in our previous step, S is the current vertex. Now the neighbors of S are A, E, and F. So we will update the distance of the neighbors. So to update, we have 0 plus 14, you get 14. Now 14 is a shorter distance than infinity, so that means we will replace this by 14 temporary. Okay, meanwhile, for S to E, we have 0 plus 9, you get 9. Now 9 is less than infinity, so we replace this by 9 temporary. And then finally, you have S going to F, so 0 plus 7, you get 7. Now 7 is less than infinity, so we replace this by 7 temporary. Okay, so this ends step 2, which is updating the distance value of the neighbors of the current vertex. Now for step 3, we will now choose the new current vertex. Okay, so how do we choose the new current vertex? So to choose the new current vertex, among the temporary vertices, we will choose the one with the lowest distance value. The one with the lowest distance value will become permanent and it becomes the new current vertex. So let's recap that. Among the temporary vertices, we choose the one with the lowest distance value. That vertex with lowest distance value gets promoted to permanent and it will become the new current vertex. So in our previous step, this one is the current vertex. A, E, and F were updated. Now it's time to choose the new current vertex. So our temporary vertices are A, E, F, C, and B. Now among the temporary vertices, the lowest is F. So according to step 3, this is replaced by permanent and it will become the new current vertex. So we can now erase this one. And we have this updated graph. Now, because we have a new current vertex, we will go back to step 2 to update the neighbors of the current vertex. So we will repeat step 2. Step 2 is update the neighbors of the current vertex. And step 3 is we choose the new current vertex. So choose new current vertex. So let's apply step 2 and step 3 repeatedly until all the vertices are permanent. So this is our current vertex. So we will update the neighbors. Notice that S is already permanent, so we can just ignore it. So the neighbors of F are E and C. So according to step 2, we update the neighbors of the current. So 7 plus 10, you get 17. But 17 is a longer distance. So this means that 9 stays. Okay, meanwhile, 7 plus 15, you get 22. And 22 is less than infinity. So this one is replaced by 22. Okay. Okay, we are done updating the neighbors of the current vertex. This time, it's time to choose the new current vertex. So among the temporary vertices, we will choose the one with the lowest distance value. So notice that among the temporary vertices, the one with the lowest is E. So according to step 3, this becomes permanent and this becomes current. So we can now erase the previous current and we have a new current vertex. Now we go back to step 2, which is updating the neighbors of the current vertex. So notice that the neighbors of E are A and C. So A and C. So we update them. 9 plus 2 is 11. 11 is a shorter distance, so this is replaced by 11 temporary. Next, 9 plus 11 is 20. So 20 is a shorter distance than 22. So this is replaced by 20. Okay. So after updating the neighbors, it's time to choose the new current vertex. Okay, let me erase some parts. So among the temporary vertices, okay, the one with the lowest distance value is A. So according to step 3, this becomes permanent and this becomes the new current vertex. So now we erase the previous current as we have a new current vertex. Now we go back to step 2, which is update the neighbors of the current vertex. So we have 11 plus 9 is 20. 20 is a shorter distance than infinity, so this is replaced by 20 temporary. Now there's no more neighbor to update, so this means that we go to step 3. So for step 3, we now choose the new current vertex. So among the temporary vertices, we will choose the one with the lowest distance value. However, the distance values of B and C are equal. In this case, we can choose any as the new current vertex. Okay, I will choose C as my new current vertex. So I will have 20 permanent. Okay, notice that it is possible to choose a new current vertex that is not adjacent to the previous current vertex. So this is the new current vertex, and the previous current vertex is erased. Okay, now we go back to step 2, which is update the neighbors. So 20 plus 6 is 26, but 26 is a longer distance, so this means that 20 stays. Now there's no more neighbor to update, so we go to step 3, which means that we choose the new current vertex. But there's only one temporary vertex left, so this one gets automatically permanent. So now that all the vertices are permanent, this means that the Dijkstra's algorithm is done. So here is a more pleasant finished product. Notice that all the vertices are permanent. Now what is the shortest distance from S to B? The shortest distance in this case from S to B is 20. Now what path must be traversed in order to achieve this shortest distance? So what path must be traversed from S to B to achieve a distance of 20? So notice that if you go from S to E, E to A to B, you get a total distance of 20. So S to E, E to A, and then A to B. Okay, this ends the discussion on our first example, applying Dijkstra's algorithm. For our next video, we will discuss applying Dijkstra's algorithm on directed graphs.